Okay, so we will get started on our new lab for the day. And that relates with the surrogate safety measures. Okay, so turn on. Okay, so we are talking about surrogate safety assessment model and how sort of surrogate safety assessment models are helpful in making safety determinations. And it was so interesting at the ITE meeting today, if you were there, they were showing some locations in the northern area of District 5, Caltrans District 5. They're showing some two-way stop control intersections that are intersecting, smaller road intersecting with US 101. And they had those stop control intersections, and then they were trying to do some surrogate safety, time to collisions, and all of that things, all of those things, trying to estimate that to figure out whether there are really safety problems with those. And actually, we did a recently, we wrapped up a research project where we looked at some solutions for those types of locations. And that project was inspired by really tragic event that happened in 2018. And it was a Cal Poly student. He was an out-of-state student from Texas, and he was riding his motorcycle, and he was riding down US 101 southbound, and on El Campo Road in the South County. I don't know if that location rings a bell at all, but in El Campo Road, there was a sort of a left-turning vehicle that from El Campo Road onto US 101 northbound they were trying to turn, and that motorcycle collided with them, and it was tragedy. The student lost their life in that collision, and it was really tragic. And there was this big controversy right after that, is that what do we do about that intersection, and which is a pretty not a good way of making decisions, right? Like, somebody loses a life and then you figure out, okay, now we need to do something. And what they did was Caltrans ended up just sort of closing down that intersection completely for left turns. And basically everybody just kind of goes like a mile detour. If somebody has to go northbound now from there, they had to go like a mile detour and so forth. So anyway, so that location still, as it stands today, there's no left turn from El Campo Road anymore because of that collision, and we just basically shut that down, which is okay, but sometimes closing intersections like that could be problematic from the perspective of, like, providing access to locations. And there was this big lawsuit that might still be ongoing right now, as far as I know, that some of the winery, somebody purchased a winery right across from that location, and then they were worried about that this is hampering access to their location because nobody from freeway can, or that expressway. Obviously, it's not a freeway because it doesn't have at-grade interchange or grade separated interchange. But so the upshot of all of that is that, closing down intersections like that is probably not the right answer for certain locations. And building a full-fledged sort of grade separated interchange, that's a very expensive affair. So is there sort of a middle ground type solution that we could look at? And that's where this project came in, is that we want to see, could we provide some alternative approaches like what we call the restricted crossing U-turn? So when you say, alternative design, what I'm essentially referring to alternative design is the RCUT type locations, and RCUT stands for restricted crossing U-turns. And then there are other variations of that, like median U-turns and all of that, and you can look them up if you're interested. But from a simulation perspective, obviously that design has not been implemented in California yet. There is no RCUT that exists in California anywhere at all. But they have tried that in the East Coast, or North Carolina is pretty far ahead on those. And then there are a couple of other places. Michigan has those as well. Yes.
Is this referring to like a jug handle U-turn?
Yes, jug handle U-turn is the same idea. They might have done it in California in some like arterial type streets, like maybe urban arterials. But as far as I'm aware, on rural expressways, they have not tried that yet. So yeah, so the jug handle is another term that is used for that. And the idea is that, and I'll show you in the presentation, but because that design doesn't exist, so there is no calibration for that, as our guest speakers talked about in the lecture today. And make sure that, yeah, so as our so they can't really validate it with anything, but simulation still provides a good approach for us to think about whether that type of design is going to improve safety, or to what extent it's going to improve safety. And that determination can be done by applying surrogate safety assessment model, SSAM as we call it. So, and this was done by Jonathan Howard, graduate student, Cal Poly, and he's now working at Caltrans full-time. He's been working there for a couple of years now. But Jonathan, some of you might know Jonathan already. But yeah, so this is sort of that work is based on. So what I've done for your lab project is much simpler. I've given you 2 INPX files, okay, and that represent one of the District 6 locations. And that was a funny thing. Also, I'll talk about that when I'm not recording this. You know, about that little story why we are looking at District 6 locations instead of looking at District 5 locations. But be that as it may, I have given you a location, a model for existing two-way stop control RCUT, I mean, not RCUT, existing two-way stop control location at Highway 41 in District 6. And then, and I've given you a vSIM model for that. And then I've also given you a vSIM model for change that design to an RCUT design. And then we're going to analyze conflicts based on those two simulation models. And that's basically what your lab assignment is. But before we get into that lab assignment, I want to make sure that you have the right background of what we are trying to do. Okay. So I'll just go through this brief presentation. So what is so I talked about that, like, you know, at grade intersections on rural high-speed expressways, they provide access to rural communities, like that winery that I talked about. And normally, two-way stop control intersections, as they are designed, they face, they face safety and operational issues. And it's very difficult and expensive to build grade separations everywhere. And that is a problem with news demand, a lot of big costs involved in that. Maybe there is not enough traffic to justify a fully grade separated interchange. So a lot of issues that we run into if we try to implement that. So we need some sort of low cost alternative to two-way stop control intersection rather than just trying to shut everything down. Okay, so that's what we're trying to do with this work. So the approach that we took was that, okay, we're going to define potential alternatives and then estimate the expected future operation, including travel times and RCUT design compared to the existing two-way stop control intersection. So we wanted to see if we implement the existing design in vSIM, calibrate and validate the behavior there, and then move on and recreate in vSIM the RCUT design. And then we explored 2 different designs in the RCUT, but I think for the purposes of this class, it's okay for you to just, so I'm just giving you 2 files, one on the existing design, one on a particular RCUT design, which somebody could model, but I've given you the model already. And then we establish a procedure to estimate safety performance of RCUT. And now I think have that process in hand, now we are able to give Caltrans staff, one more tool in their toolbox. So they can look at RCUT as an alternative, as a potential alternative for that. So what is an RCUT? It's basically a design limit, a design that limits the maneuvers to reduce conflicts. So here is what you can see. So here is what you can see here, that instead of having sort of a through movement from the straight from the minor street. Anybody who needs to turn left, you make them go right first, and then get on this left turn bay and then make a U-turn. Now, what you're doing essentially is not eliminating the conflicts. You're not necessarily eliminating all the conflicts, but you are trading some conflicts that might have been of crossing type, where you could have really fatal type collisions, because you had that maybe a T-bone occurring, or a 90-degree angle collisions that are happening. Instead of those, now you've traded them off with collisions that might be more, or conflicts that might be more of merging type. And we know that merging conflicts tend to lead to less severe collisions compared to crossing conflicts. So basically, the idea of RCUT is you trade away the crossing conflicts, and now you only have merging conflicts. That's the whole idea of it. Oh, by the way, RCUT, a lot of times you will see a lot of federal highway documents and even Caltrans documents, like when they talk about alternative designs. Maybe not quite Caltrans documents because they don't have RCUTs or anything implemented already. But if you look at a lot of state DOT documents and federal highway documents, they talk about alternative intersection designs. So they will put RCUT in that same class as they would put the diverging diamond interchange that our guest speaker talked about in the lecture. So all of these are sort of classified in the broader category of alternative intersection design, where you're doing something, for the lack of a better word, something funky than a traditional sort of cross street design, right? And then they work in a lot of contexts. They could work. Obviously, they don't work very well. They could be problematic from a perspective of a pedestrian or bicyclist. So you have to kind of look at the context. Obviously, in a District 6, District 5 rural locations, we don't have a lot of bicyclists or pedestrian traffic, which is why this could be good options. And again, there's some research that's ongoing about how do we make sure that if we implement DOT in urban streets, how do we account for movement of pedestrians and bicyclists and not just sort of prioritize the car movements. But again, RCUT sort of fall into the broader umbrella of alternative intersection designs. And then all side street traffic must turn right, make a U-turn downstream to go through left. And then mainline left turns, sometimes you leave the mainline left turns as they are here. So you're allowing the left turns from the main line in this design that I'm showing you, but there are some designs that don't allow that. So you could have RCUT design that makes even the left turners from the main line to be part of that U-turn design. And that just depends on what's your relative flows, how many vehicles are trying to make that left turn, if they have enough gap and whatnot. So there is a lot that goes into it. So this is, I think, let me see. So this is sort of like a VISIM video of, it's not going to work. Okay, so this was a VISIM rendering of 3D rendering of an RCUT intersection. I believe this video was from, I'm going to play it for you. I can't quite play it from this slide, it's this Google slide, but I can play that video for you if you're interested. It's just a short video of US 101 in Tasahara Creek Road up in North County, San Luis Obispo. And that's a very challenging geometry, so RCUT actually would not work there. But we were looking at some potential locations in District 5 too. But that's this one. I'll show that to you later. And we looked at 5 different locations, 3 in San Luis Obispo County, 2 in California Central Valley. And you could see that we had input from our local MPO for the District 5 locations, and then from District Caltrans District 6. And again, it's the probably when I'm not recording, I can probably tell you a story why, but we don't have input from Caltrans District 5. And even though we love some folks that work there and all of that. So, okay, so this is the location that is part of your lab assignment. Location 4, that's what I'm focusing on. And this is the existing geometry of that location. You have California 41, which is your rural expressway. And then this is what that looks like. And you can probably anticipate the problems here, right? I mean, you have the side street traffic coming to a complete stop, and then basically trying to cross in that high-speed gap. There's a lot of potential for those crossing conflicts that could be leading to more severe collisions. So they've had, fortunately, they haven't had a lot of collisions here, 7 crashes in 3 years. none resulting in severe injuries. And that, I think, is a testament to how safe the vehicles have become. Vehicles themselves, the cars that we have nowadays are very, very safe, at least for the occupants of the car. Maybe they're not as great as for people who might be outside of the car. In fact, they're becoming less safe for the folks who might be outside of the car. But even with several crashes, we haven't seen a lot of injuries happening here. But again, there is potential for injury here because of those crossing conflicts. So what we did was like we modeled that location as it exists, and we inputted like the 2020 traffic volumes, and then we did like 2030 volumes, like based on some projected growth rates and stuff like that. And then we modeled different RCUT configurations in VC as well. And then we calibrated them by recording the video at that location, looking at the gaps, made sure that we are capturing the gaps appropriately. I know, Blake, you helped out with some of that data collection for District 5 locations back when we were doing it in 2020. But this location, District 6 locations, was great because they had automated data collection for these locations. So they were able to just provide us with the video. So that was great too. But so we analyzed a bunch of scenarios, 2020 data, 2030 data. We looked at 3 different RCUT design. We looked at AM, noon, PM, and weekend, because some of these locations were really experiencing high traffic during the Friday evenings from the valley coming to the coast. And some locations had the other way around, where like, the Sunday afternoons were pretty busy. So we looked at wherever there was high traffic, we looked at those time periods. But your scope of your project is fairly limited. But this is sort of the idea, is that one RCUT design that we evaluated was that, that doesn't have the median U-turn. So you don't see, so there's no U-turn here. I mean, there is all U-turns. So everybody has to U-turn, even if you're a main line, you want to get to the side street, you have to kind of come back and make a U-turn. And this one does allow the practice of like making a U-turn from here. So we looked at both of those designs as well. But for your purposes, so this is, so now I want to go back to your lab assignment. So you'll review these slides, and then I've provided like INPX file to generate the trajectory data. And I want to show you how do we use this to generate the trajectory data right now. So if you look at, go ahead and open the files that I've provided. I'll go back. And again, you probably need to build these models. And so I'm just showing you. So you don't even have to analyze the MUT part, but you just have to take this. This is the existing design. So I'm going to download that file. And then I want to download the RCUT design. So these 2 INPX files that I just downloaded, those are the 2 files that we'll be using. But so let's open these files up now. So in recent output that we have generated so far, we have not yet generated the trajectory files. So what I'm showing you right now is to show you the trajectory files. This is the existing design. You can see that. So this is what it looks like right now as it exists today. So there's all these routing decisions and all of that. So if I hit enter, hopefully, yeah, so traffic is now starting to move. We can speed that up, hopefully. Just trying to see. So it's still running. The traffic simulation is still running. Oh, because it runs multiple scenarios. So I can probably just stop that. So now, if you go to the download folder, I go to the download folder now. Oh, it generated. Oh, okay. So it generated what we call a TRJ file. And again, this is running multiple scenarios or multiple seed numbers. So if you go back and look at the simulation parameters, it's running random seed 42 and it's running five different scenarios, and then we incremented that by 86. I don't know why Jonathan did that, but that's okay. Doesn't matter what that number looks like, but it's running five different sort of random runs, and then you can average the data. For every run, there is going to be a TRJ file that's going to be created. Now that does not get created by default. Again, it's a big file that gets generated every time, so they don't want to generate it by default. But if you go under evaluation, so if you run any of your models that you've developed so far and run it, you probably have not seen a .trj file in your network. So if I go back here and run some of the older ones, so maybe this 529 lab 2 file, if I open this file and try to run it, it won't actually generate a TRJ file. So I want to show you how to get that going. So if you yeah, so we'll just try to run it. Yeah, it's fine. So if I stop it now, I look at my download folder. So see, it for the 529 lab 2 file, it only generated the RSR or the ATT file, but no TRJ file, as it did for the 41 existing PM network, right? And how do you do that? How do you get the TRJ file? This is what you do. So if you go to evaluation, configuration, and direct output, you have to check this box for SSAM. So let me highlight that box. I can escape and then annotate it. So this is what I'm annotating. So this is the box you need to check. This is the box you need to check here. SSAM. This one. So if you do that, then that's the cue for vSIM to be able to create the trajectory file. Now, if you click on more, like if you have a bigger network, you can, I don't think this is going to be allow you to do that by section, but in the full version of vSIM, you can actually, because the TRJ files are so large, sometimes you have bigger network, but you're interested in only a portion of the network, you can generate a TRJ file just for a portion of the network as well. And this is where you specify under more. It's not letting me do that right now because we have a limited version of the software, but that's another possibility. But for this lab, you won't need to specify that. You can just run it for the whole network. It's a small network, so you're not really interested in what's happening, and you wanna get all your conflicts for the whole network anyway. Okay, so all you need to do is check this box. So if I go ahead and check that box for this other file now, so if I go to evaluation, configuration, and I go to direct output and I click on SSAM, I hit OK. And if I now run this file, which is lab 2, like an old lab 2 file that I had, I save the changes. And then once you go back to the file here, see now, this TRJ file is getting generated. Okay, so it's updating that TRJ file as it's running. And then I think hopefully you'll see the file size go up as well once the model has run. But that's the idea. Okay, so once you have those TRJ files, what do you need to do? You have to do a very simple thing. You have to just take the 2 TRJ files that I've given you, and you have to give me the results in the Excel file, and I'll create that for your submission. But if you go back to the all you need to do is, this is the lab. So use the attached INPX files to generate trajectory files. And then we described that in the lab today. So I'll have this video available to you. And then an Excel file showing the number of simulated conflicts in both trajectory files, a short paragraph to explain the results in the context of existing 4-legged and the proposed RCUT design. So if you open the second INPX file, so RCUT PM, if you look at this one, this is what the RCUT design looks like. So in this RCUT design, I'm allowing the left turn from the main line. I'm allowing the left turn from the main line. Okay, so that's what we call RCUT PM. And then you could have one where this is not allowed, but I'm not. You don't have to worry about that portion. So in both of these files, actually, if you look at the evaluation configuration, the direct output box is already checked. So that's what we're going to make sure that .drj files get generated for an analysis. And then once you have the .drj files, you take them to another software called SSAM, which is the Surrogate Safety Assessment Model. So it looks like, because we don't have a tech anymore in the civil engineering department, sadly, a computer person. So it's all sort of centrally controlled by ITS. It's very hard to get any of these softwares on this. But the good news is that SSAM software is from Federal Highway and it's freely available. And you can install that on your even personal Windows machine. So what I've done is, and it's a very quick software to install. Let me see if, I don't even think it's on here either. Yeah, no, I don't think we have that here. Yeah, we don't have it on this machine either, and they don't allow me to install it. But I give you the surrogate safety assessment model. You can input the trajectory file as a whole into the surrogate safety assessment model. Use the default threshold that it has, and I'm going to show you what those look like for the post encroachment time and for time to collisions. Remember the two measures that we talked about in the surrogate safety discussion in the lecture on Tuesday? No, was it Tuesday? No, Tuesday we talked about two fluid, but the last Thursday really, when we talked about surrogate safety assessment. So you'll leave the threshold as it is, and once you hit OK, it will generate for you the data that you're going to use for Excel, or that you're going to fill up the Excel file with. So this is what I'm looking for ultimately. So you don't have 4 different scenarios. I just have like 2 different scenarios for you. And I'm just looking for crossing, rear end, and lane change conflicts. And these conflicts will be generated by using the SSAM. And SSAM I've made available to you. So you'll have to use a Windows PC that you can install software on. So if you click on this and download this, let me see if they let me download it here. Maybe they do. Let's see. So I'll try to do that. In the meantime, I was looking for. Yeah, so microstimulation. So we talked about it 1 week ago. So if you look at that SSAM interface, this is what it does. So this is what you're going to see in the model. You can see the bottom. It's classifying the crossing, rear end, and lane change conflicts here. So let me just kind of take my mouse there. So crossing, rear end, and lane change. So SSAM will specify that in the summary of conflicts. Okay. So it's trying to estimate how many times vehicles got closer to each other than 1.5 seconds, or post encroachment time of less than 5 seconds or something. So they're looking at that, and they have angles specified for what's a lane change conflicts, what's a rear end conflict, and so forth as well. We saw these. So based on this, I think the defaults that you see are going to be 30 and 85. But let me see if I can. If I click on this. So let me go ahead and pause the recording. So all I'll do is like, I'll try to install it in the next few minutes if I can install it. I don't think they let me install the software before, but maybe I did ask them if they could. Haven't heard back, but I'm going to try it to see if I can install SSAM. You will need a Windows PC where you can install software for it. If it doesn't work for you, I can, you could have it analyzed using, one of the software. It's a very easy software. You just have to load the TRJ file and you get it. Now, one thing that you may be wondering, like, what about the seed numbers? How do we use the seed numbers here? So we can't use, like, it doesn't take multiple trajectory files at the same time. So SSAM is like a federal highway software. That's like, it's not very well maintained. I mean, it's there, they update it, we are at version 3.0 now, but it's not a software where they are really interested in keeping it up to date in terms of like, okay, if I want to have the average number of conflicts from 20 different runs, there's no way to do that. So the only way to do that is like, input one trajectory file by one trajectory file, get the conflict number and then average them out. But it's okay for you all to just enter one trajectory file from one simulation run and report those numbers. But I think a good practice would be to, again, input 5 trajectory files, get that simulation data for 5 different runs, and then get the conflict data from those 5 different runs and then average out those conflicts. So that would be the best way to approach it. But for your lab assignment, just doing it for one seed number is perfectly fine and acceptable. Okay. So I'm going to stop talking for a few minutes here. So I'm going to at least pause the recording. Resume recording. Okay. So you download the SSAM master, you double click on it, go here. Okay, and then SSAM3. SM3EXE, yep, that's the one you go to, yep. And then scroll all the way down. And I'm recording this, so you don't have to. And then you click on this SSAM3. And then you extract all and run. I guess you run. No, you don't run it, okay. You extract all, I guess. Okay, and then you let it extract and everything. I think, let's see. And then that gives you this access to this SSAM. Yeah, that's exactly what it looks like. Yeah, this is right. I don't know, it takes me to this Visual Studio weirdness. So I'm gonna, once you install it from that tab, you have to search for SSAM on your installed directory and then go to apps. And then this app should open. So you say no for App Store and then SSAM3 should open. Now, once you open the SSAM3, you can just add any trajectory files to it. And then these are the locations, these are the items that you enter. So forget about this. Okay. So once you open this folder as SSAM3 application, you can add trajectory file. You can go and then maybe under downloads, I had those trajectory file. So I can just hit open and analyze. And then you could change some default values, but I think for now we can just leave the default values to be same. If you make the default values larger, what that means is that now you are basically counting more conflicts. So even when vehicles come within 2 seconds of each other, count that as a conflict. Okay. But if you make it, so you're basically becoming more conservative and counting more conflicts. But if you make it a smaller value, then you're counting fewer conflicts. Okay. And then maximum post encroachment time PET, same thing. The larger value implies that you're going to count more conflicts, because even when vehicles come in within 6 seconds of each other, you count that as a conflict. If you increase this number, you can leave the default. This is the click here for the conflict diagram. This is the diagram that you all saw in the lecture that we did last week. So there is 30 and 85 here, but here the rear end angle is called 30 degrees. Crossing angle is called 80 degrees. And you can change it if you need to. And then you just click on analyze. Then it starts to process that trajectory file. Whenever it's done, analysis is complete. And then you can look at summary. So you can see that I did not let it run the full time. So I see 1 crossing conflict, 1 rear end conflicts, and 3 lane change conflicts. Okay. So that's the report that I'm looking for. Okay. Now you can actually take the conflicts, and then this is sort of gives you all the details of the conflict. So you can export that into a CSV file. Again, you don't have to do that for this lab, but you can find for each conflict, what was the you can figure out what's the length of the vehicle. So this first length and first heading, these could be useful. The length could be useful to figure out whether you have a bicyclist or pedestrian involved in a conflict or not. I mean, this is all cars in this project, so it doesn't matter. But these could be very good filtering mechanisms to figure out which conflicts include pedestrian and bicyclists. And we are doing that for another project where we're analyzing this for the city of Atlanta. So that's something that you could look at. But again, we don't have to worry about it. But for now, I think your thing would be completed with the summary. You just have to take the complete trajectory file and report these numbers for me. Because these are all unfiltered, so you're going to get the same number in both the rows. And that's the number you need to report in the Excel file. So you just need to report 1 for the base conditions or the existing condition, 1 for the new condition. Okay. All right. So let's go ahead and work on that too. This is going to be due next Thursday before the lab. Hopefully you'll get a chance to work on it. And then we can work on the 2 fluid lab when we meet next week. Okay. All right. Thank you guys. I'll stop this recording here. And again, if you have any questions about the lab, about the homework, about the project, please let me know. We can address those.